Okay, there's still a few more people entering, but welcome to the seventh seminar on Computational Physics Challenge. Tonight it's on numeric calculus methods. So I hope you've had a little break over half term, but managed to think about some of these things and try them out for yourselves. That is the essential way to developing the skill, to try it out and give it a go. Then you can ask questions about it. Okay, so let's start off, and I'll just pass over to Dr. Andrew French. So thank you very much.
Okay, good evening, everybody. Welcome back. Great cracking question from the Q&As. What is numeric calculus? So please stick with it, and hopefully that will become nice and clear. Calculus is the magic method of maths, which if you haven't yet experienced this, this hopefully will be a bit of a revelation for you. Firstly, so basically calculus is split into two parts. Firstly is the finding of gradients. So pretty much all the laws of physics are defined in terms of a gradient of something rather than the something itself. You know, the Newton's second law, mass times acceleration, is the vector sum of force. Acceleration is the rate of change of velocity. So pretty much everything you'll find will be defined in terms of a gradient, either how something varies with time or how something varies with distance, like sort of forces, etc. So this first half is about how we can find gradients, but how we can do that numerically. If you've studied some calculus, there's a huge amount of wonderful maths that we're not really going to get into actually today. I'll leave that for your mathematics lessons. This is really about the tools where we can basically support our calculus investigation with spreadsheets and code in line with the rest of the course. But hopefully we'll give you some nice examples of how we can use calculus in our sort of physics and wider science piece. So first bit about finding gradients, which we call differentiation. So we're going to start off with this guy, Usain Bolt, still the world's fastest man. So in London 2012, Olympics in London, so Bolt won gold in a ridiculous time of 9.63 seconds. That's for 100 meters. When he set that, the world record was even more ridiculous, which he set in Berlin in 2009, which is at 9.58 seconds. And I confess, in my youth, I used to do a bit of sprinting, and I just about snuck under 12 seconds. So believe me, this is a ridiculously fast time. The question is, well, we've got this, but how fast did he go? And indeed, you know, what does that statement actually mean? You know, is it 100 meters divided by 9.58 seconds? Well, that's an average speed. But what does that tell you about the dynamics during the race? You know, did he pull away? Did he slow down? So when we're looking at this, and this is a nice way, and this is how I always start teaching kinematics, which is the Greek for kinema, or motion, movement, which is literally the study of motion. And I mentioned Newton's second law a little while ago. That's probably one of the most fundamental laws of mechanics, that we can relate forces on the sort of right-hand side to mass times acceleration, which is kinematics scaled by the mass or inertia or something. So if we know the forces acting upon something, we can work out how it moves. So the kinematics, acceleration, velocity, displacement, are really, really helpful. And so we'll start this little discussion about sort of really pinning down those things. Okay, and the nice thing is we can use a 100-meter race to make sure we're really sorted about those definitions. So we're not talking about movement in 2 dimensions, although Usain Bolt's 200 meters, you could argue, is even more impressive, about 19.28 seconds, I think. Actually, no, I think it's quicker than that. I think it's 19.13. Someone can check it for me. Okay, so in kinematics, we're really defining motion by a graph. Okay, so displacement versus time, velocity versus time, and acceleration versus time. And remember, these things are vector quantities, arrow quantities. Okay, although in the case of Usain Bolt, that's an arrow starting at the start line and going towards the finish. You know, if we were going around a bend, we'd have to be sort of moving our arrows. So displacement x is the position vector from a specified origin, i.e. the start of the race. And then velocity is the rate of change of that vector. which in our case is going to be just in a straight line. So if we plotted a graph of displacement versus time, our velocity is going to be the gradient of that graph. And acceleration is the rate of change of velocity. Again, that's a vector quantity, but in our case, it's going to be the gradient of a velocity time graph. So there we are. Although these things are vectors, for simplicity, we're going to look at just one dimension. So let's have a look at Usain Bolt's race. So a very nice, I think it's an Australian chap, spent ages looking at Usain Bolt's 100-meter race during his world record. Well, it's the it's the world record he beat in Beijing in 2008. Where, if you're as old as me, you'll remember he threw his hands in the air in amazement and still managed to cross the line in a world record time of 9.69 seconds. Whereas in 2009, he sort of had his game face on and went through the line without slowing down very much and got the world record to 9.58, which, as far as I'm aware, is still the world record now in 2022. So these are perhaps the two fastest races ever. So what someone has very nicely done is every 10 meters worked out where he was in time, as it were. So what is the time as he crosses the 10-meter lines? And if you look at a video of a track, you can't quite see it here, there's a sort of bend during Usain Bolt's sort of characteristic move. You'll see a line every 10 meters. So you can inspect the video and you can do this quite accurately. Now, ideally, we'd have the time every meter or every centimeter, but so there's a bit of approximation with the analysis, which is going to carry on. But hey, that's probably something similar to what you'll do in a classroom if you're a student. So if we plot displacement versus time, what are the obvious features? Well, for starters, it's going to end up going from 0 to 100, all right, because it's a 100-meter race. So the time difference, and there's a very small amount you can see between Berlin, which is in the red, and Beijing, which is the black one. It looks a very, very similar curve, and it's a curve, so the gradient is not constant. So the gradient's increasing, and then it becomes pretty constant. And if you look really carefully, especially the Beijing one, the gradient starts to diminish a little bit. However, it's quite hard to tell the difference between these. So you could argue that a displacement time graph isn't really the right graph to convey meaning about Usain Bolt's kinematics. And certainly, when we're doing analysis like this, the velocity time graph, the gradient of this, it's in the middle, all right? That's probably the graph that gives you the most information. So how can we get velocity versus time from this? And it's important to note, I've not defined any formula for this graph, all right? So if you were doing some calculus, you might have something like, y equals x squared. What's the gradient of that? Right? The answer is 2x. But we're not going to get into that. We're going to actually take some data and sort of do this numerically, hence the title of the course. So we could have any relationship you like. As long as you can make a curve through these points, we can figure out the gradient. So how might we do this? Well, if we were doing this with a ruler, so if you've sat your GCSE exams and looking back in a sort of rose-tinted view of those, or you're about to sit them, I guarantee you will have a question which has some sort of curve. It's usually a cubic, and they'll ask you to work out the gradient with a ruler. So you'll do a nice tangent to every point, the biggest triangle you possibly can draw, and you'll do rise over run, all right, and you'll work out the gradient. And if you're feeling really sort of snazzy, you realize I can do this with calculus, and you can work out precisely and make sure your answer is correct. A little top tip for you there. However, in our case, Usain Bolt's not following a what we call an analytical curve. He's just running as fast as he possibly can. So we're going to work out what the gradient is. So what I've done is I fitted a series of what we call cubic splines to these points. This is a cubic function, so every 4 points, and it rolls. Now, a cubic, I can work out the gradient of that. The law of calculus tells me that's a quadratic. All right. Again, I'm not going to do a sort of calculus course today. It's more about the numerics of it. The point is, if I've got a cubic function, I can always work out what the gradient of that is. So if I fit this nice series of cubic curves using something like MATLAB, I can work out the gradient at any point. So I can work out delta x over delta t at any point I like along this line. All right, but essentially it's the same process that you would do by eye, taking a tangent to the curve and working out delta x over delta t. And remember that although that triangle is huge, it'll be a different triangle for every point. Okay, so at this particular one, he's going at an amazingly fast 11.2 meters per second. Right, so what does that mean if I was to do that at every point? Well, I end up with this. Excuse me. So I've got a few caveats to this. Now, he's clearly not starting from 4 meters per second. You know, he does start from 0. However, we can assume he kind of explodes out of the blocks. This is a problem with the small number of data points we've got. So to sort of fit a nice curve, I've sort of set the velocity to be this sort of reasonable amount at the beginning. Okay, but in general, of course, there will be a sort of rapid acceleration as he explodes out of the starting blocks. So what can we see from this? Well, this now reveals loads of information. So for the first sort of 2.5 seconds or so, Usain Bolt's accelerating. In other words, there is a gradient. The velocity is changing with time. All right, so the gradient of the velocity time graph is the acceleration. All right, so this is in the middle. So we can sort of really understand his dynamics from this graph. So he's accelerating, and in fact, the accelerating is getting larger as he goes, as he gets into his stride. And then something weird happens. So in the Beijing one, in fact, it's not the Beijing one, it's the Berlin one, the 2009, the actual world record. It seems like he actually slows down a little bit at about 2.5 seconds. Now, this could be numerical noise. What do I mean by that? Is that you look at our data points, there's not that many of them. So it could well be this is an artifact of me trying to fit some curves. However, as I said, I used to be a sprinter, and what can sometimes happen is you can actually stand up rather too rapidly when you're driving out of the blocks in a 100-meter race. So it could well be that even though he ran the fastest 100 meters ever, that could have been even quicker. All right, so you'd have to look at the race really carefully at about 3 seconds and just sort of see whether maybe his head went up a bit too quickly. So he accelerates a little bit more, reaches a top speed of just over 12 meters per second. And then he maintains that for, well, 5.5 seconds, not 4.5 seconds. And unlike 2008, where you can clearly see him losing about 1.5 meters per second as he slows down and puts his hands in the air, in Berlin, that doesn't happen at all, and he cruises through the line. So this is a result which I've told anecdotally is true of sprinting, is that if an athlete sort of pulls away from the crowd, it's not that they're actually getting faster than the others, it's just that they're slowing down less. So if you were to try and want to analyze that statement, you'd have to have lots of different curves for each athlete. And what you probably find is that the athletes that are not winning the race actually slow down a little bit, whereas the winners will probably hit their top speed and maintain it. So that's something that you could think about. And if you were an athlete, these graphs could be really helpful for your training. Particularly, could we make sure that bump doesn't happen? You could also use this to maybe analyze how fast Usain Bolt could go, or perhaps how fast a human could go. Is 9.5 seconds possible for 100 meters? So there's a whole science of sort of human performance and kinematics, and we can widen that to non-human performance, cars, bicycles, rockets, by this analysis. So the velocity time graph I commend to you is the sort of the golden graph to plot. So what do we have? So the gradient of that will give us acceleration, which we'll look at shortly, and the area under this will give us displacement. And this will link to the second part of our talk tonight, where we talk about integration, the areas under curves. So it's the reverse process of differentiation, of find the gradient, which is integration, find the area. So let's go for more differentiation. Let's find out what the gradient of this graph is. Just a quick question. World record made in 19.19 seconds in 2009. Thank you very much indeed. Outrageous. That's amazing. Okay, so there we are. So let's have a look at the gradient of this graph. Again, we're using the same technique. We're fitting cubics. The reason we fit a cubic, well, if you fitted a quartic or a pentic, you're using rather too many data points. So, we wouldn't be able to fit very many. So a cubic gives you a little bit more precision to fitting, different curves. You could fit a quadratic, but the cubic's a nice sort of compromise. Okay, so we're fitting a cubic between every 4 points, a rolling 4 points, and then that is the curve that we're using, or a series of curves. So if we take the gradient of our velocity time graph, we get the acceleration versus time graph. So our second derivative, if you like, the gradient of displacement versus time. Now you can really start to see the numerical noise in this. So this is, and I'm going to use that phrase quite a lot because the ups and downs here aren't really physical. We've only got a small number of data points. So the fact that this is above and below the axis is not really relevant. So what we can see though is the acceleration peaks at about 5 meters per second squared after about 2 seconds, and then rapidly drops. And then essentially Usain is running at constant velocity. And we know that's because the acceleration is essentially 0. There's a bit of wiggle around it, but to be honest, this paucity of data points mean that we can probably ignore all of this. Right? This is an error in our analysis. However, we can see in 2008 a deceleration that definitely happened in the last couple of seconds, and that's at about 1.5 meters per second squared. So there we go. And this graph, of course, now relates to force, because mass times acceleration is the vector sum of force. There is a song with this in, which I'm not going to play for you now, but I can give you a link. And I hope that will become an intensive earworm. There we are. Maybe I'll play that over the video to conclude tonight, if Mr. Hughes will allow me to. So there we are. Anyway, so what we can do is we can multiply this graph, all points on this graph, by that Usain Bolt's mass. I don't know, maybe he's about 90 kilograms, maybe 100 kilograms. I have to find out. And then you will have the force, the vector sum of force on Usain Bolt. So that's really useful because you can work out how many newtons his muscles are working on him against not just against gravity, but propelling him forward. And then you could use that to work out sort of muscular strength. You could maybe devise a strength training program. So from the kinematics, we can find out all sorts of stuff about how we can produce that kinematics with forces. So if you were a car designer or a bicycle designer, or looking at animals, or about anything that moves, finding the acceleration time graph tells you about the forces. Okay, so here we are, putting those together, we have a little flow. So this is displacement versus time. Notice I've got the same time axis. All right, so we can compare like with like. But the y-axis is different. So if I'm taking the gradient of this graph, I've got this one. I take the gradient again, I've got this one. If I take the area under this one, I've got this one. If I take the area under this, I've got this one. So differentiation goes from displacement, velocity, acceleration, and area under a graph, which we call integration or anti-differentiation, goes the other way. So calculus is a kind of circular process. Find the gradient is what we call differentiation. Find the area is what we call integration, and we can go backwards and forwards. Anyway, if you're new to this kind of stuff, I think it's a really good idea to have this model in your mind. So think Usain Bolt, think the 100-meter race, and then hopefully you'll get an understanding of the gradients, so velocity, acceleration, and with a bit of help, possibly going the other way, which will be the road for integration. So the area under our velocity time graph is how far Usain Bolt's gone. All right, so the area under this graph will be precisely 100 meters for both curves. Right, I think there's no more questions, so I'm going to move a little bit on. Aha, can we find the force with acceleration time graph, but V time graph is also usable? Therefore, which graph would you say is the most accurate and useful one? Oh, right. Okay. So if you've got, well, I think I'll try and answer this question with a different analysis and see which you prefer. So on the 20th of July of last year, the world's possibly second or first richest man, a certain Mr. Jeff Bezos, who even today, I think I gave you some more money by buying one of his books, launched himself and some others into space through the Blue Origin rocket. Why have I put this up here? Well, basically, if you look at the video for this that was released, we won't look at that today, but you can find it on YouTube. In the corner, they have altitude, so the height from the Earth, and velocity. So I spent a happy hour or so transcribing that information into an Excel sheet. So let's go and have a look at that Excel sheet now. And you can access that yourself if you've downloaded the zip file. So it's a file called New Shepard, which I think is a homage to Alan Shepard, who's one of the original astronauts. So that's Bezos's team. And so this is the time in seconds. Well, it's what I've got here. The altitude in feet, and I've worked out the velocity in miles per hour. Okay, so I've converted those things into kilometers, make that a bit bigger, in altitude, velocity in meters per second, and acceleration in meters per second squared. How have I done this? Well, if you look back to the presentation, if we go to this one, what I've done is this is a very sort of simple way of finding out the gradient between 2 points. So in this case, we've got quite a lot of data points. So there's no real need to fit a cubic spline or anything complicated like this. All we're doing is working out the difference between a velocity measurement and the previous one, and the time and the previous time. And I think in this case, the times, and they're not quite the same. I think I got bored and didn't quite do it every regular time interval. So let's just have a look how we've done that. So if we got here, New Shepard. So here we go. So 15.47. So if you look, it's I9, which is that velocity minus the previous velocity. So 92.98 minus 15.65. That's the change in velocity. And the change in time is D9 minus D8, which is this one. So that's going to be 24 minus 19. So there we go. So we can get an estimate for the acceleration based on the change in velocity divided by the change in time. In this graph, it will literally be drawing a triangle between the 2 points. Okay, clearly that's not quite accurate. Be better to draw, to make a nice smooth curve. But if we've got enough data points, that's gonna be all right. So how have we done? So if we plot some displacement, acceleration, velocity, and acceleration, we get these graphs here. So what can we tell? Well, we have this sort of sort of an upside down smile trajectory. Bezos reaches, I think, goes beyond the von Karman line, goes over 100 kilometers beyond the Earth. And but what's perhaps more interesting is the second graph. You'll notice this is an inverted parabola, and the gradient of a parabola gives you a straight line graph. So what's the gradient of this? Well, that should be G, right? Because he's in free fall. Now, G will be a little bit less at height than 9.81 meters per second squared. But the idea is that for quite a lot of the orbit, so this is what, about 300 seconds or just under, that the spacecraft is essentially in free fall. So the astronauts will feel weightless and can float around and all that kind of stuff. There's an interesting sort of kink here. I'm not quite sure what that means. I think there's some sort of I don't know. There's either some sort of maybe. I know I'm not going to speculate. I think you'll have to sort of drill down what that means. There's some sort of acceleration. You can see by taking the gradient of this graph that there's a sort of deceleration at this point. I don't know whether it's the separation of the craft or some sort of braking system. We'll have to see. Anyway, you can see here that the acceleration is pretty much spot on G, so minus 9.81 meters per second for this part. And then there's a bit of a positive acceleration as it enters, as it sort of re-enters. So there we are. So yeah, so it's sort of falling in, then you'll sort of brake a little bit. And there we go, there's our acceleration. So yeah, so there we are. That's another example of our kinematics. Can you give an example of where a Taylor series would be used? Right. Well, I mean, that's a bit different, really. I mean, and a Taylor series is where we're maybe, say, fitting a quadratic around in the vicinity of a point. So we might say at this point here, we can fit a quadratic and that's the sort of curve, that's the polynomial we can find about this. But we're not really interested in making, an analytical model of what's the curve throughout time. This is the data, this is what happened. All right, all sorts of things like that little strange glitch there. This is reality. What we want is to actually go from displacement to velocity to acceleration. We may not know what the underlying model is. There may not be an underlying model, but we do want to find out what those gradients are. Okay, so
sorry, Andrew.
Go for it.
Sorry, Krish has a question. How do you find the equation of the curve?
Right, as like I said, so we in this particular case we are not in the business of finding out what that equation is, because if you've got an equation like minus x squared, something like that. Let's go back to this. Let's make that nice and big. That might be true of sort of throwing a projectile, an apple up and down. Bezos's curve there might look a little bit like that, but actually there's no reason to fit something. So give me the altitude at time t. What is that function? We're not in their interest in that. We've got the data, and we'd like to find out what the gradient of that curve is, i.e. what velocity versus time is. And if we know velocity versus time, what the acceleration versus time is. Okay, so although it's helpful to for problems, etc., to find out a model from reality perspective, we may not need to have, there might not be a model, but nonetheless we want to find out what the gradients of curves are. So that's a sort of Bezos example. Here we are. Here's a sort of more expanded view. Whoops. There we go. And there's our acceleration, which is the change in velocity over the change in time. So notice, if we had data, we can always work that out with a spreadsheet. All right, so we can always do some calculus approximately using a finite time difference, regardless of whether we can actually work these things analytically. All right, i.e., using mathematics to tell us exactly what the gradient's going to be. So here we are. So kinematics provides a really good reason to wish to know velocity or acceleration from displacement measurements, i.e. the gradient of the underlying curve. We may not know the functional form of the curve, however, we may have to estimate it from the data. So this may be uncomfortable for some of you who have just been doing pure maths, but remember, we're trying to apply pure maths to reality, but we can't bend reality to our will. That's wrong. Reality, is well, as in your philosophical position, but we get to see a glimpse of reality, and our models and our rules are approximations of it. So there we go. So in the two examples, we've assumed a straight line between our velocity measurements, and the bolt example, we fitted a cubic between those, which gives us a slightly sort of a more precise way of doing it. Okay, so another example where we might want to do this is very, very current at the moment. So I'm not going to go into the details too much of this. I'll save these for the final number 11 lecture. Please come to that one. That will be the final one of the course, where we'll talk about epidemiology. But in essence, the World in Data website run by Oxford University has been mapping coronavirus and other things since the start of the pandemic. It's a really incredible data set. And probably the most reliable thing, I don't think I'll say anything controversial here from that website, is the recorded deaths from coronavirus. And so these are in thousands for the UK since the start of the pandemic. And you'll notice it forms this series of S-shaped curves. Now, when we're talking about epidemics, probably the most sort of intuitive thing to imagine is the number of people who are infected. And at the start of the pandemic, the government was talking about, flattening the peak and making the peak lower, all those things. But you can see from this graph, there isn't a peak. So what were they talking about? And I think what they were talking about is infected versus time. But of course, even with comprehensive testing, that is going to be an estimate. So how could you go about estimating the number of people who had a virus? Well, all we've got really that's reliable is this cumulative curve of those people who've perished. Or you could have a much larger curve for those who've had the disease and maybe recovered, but we might not know those. Although there are some huge difficulties in achieving this, In the UK, if you have died of coronavirus, you'll be logged. It's a pretty gruesome statistic, but that's an important one for trying to manage these diseases. Now, in epidemiology, the rate of change of the dead essentially is proportional in the most simple model to the number of infected. All right, so this equation here, that little d there means a small change in d divided by a small change in t. This is Leibniz's notation. It's essentially the little triangle we saw before, the rise divided by the run. And we shrink that triangle to the smallest possible time interval we can think of, like a magnifying glass on this curve. Now, we can evaluate the rate of change of that in a very similar way that we did for Bezos's data. I've done a slightly more snazzy way of doing this. I've gone from n+1 to n-1 to evaluate at term n. So I've gone sort of forward and backwards by a day, as it were. That's just a slightly more precise way of working out my triangle. Now, what's k and what's alpha? Well, these are parameters in terms of the sort of mortality fraction, which is k, and alpha, or rather 1 over alpha, is proportional to the amount of time it takes for once you've been infected to either you pass or you recover. And now these things it's important to note are really approximate, and you have to guess these. It's also important to note this is the simplest, crudest model of epidemiology that I can think of. So please don't take this as chapter and verse. Go onto the NHS websites for all of that. However, I think it is worth noting that to get this graph here of infected versus time from this is not always that clear. They do have something which looks like this on the World in Data website, which they could have, it's the sort of, rate of change of D, basically with time. So it's essentially a scaling of this graph. But this is how you can calculate it. Now, with some estimates about, I think we'll qualify that, guesses. So if 1% of the people who get coronavirus in the first wave, this is pre-vaccination, remember, unfortunately passed, and this alpha parameter is about sort of 1 over 9.32 days, then what you can do is you can work out or estimate the number of infectives from this curve. And I think that's actually quite a powerful figure, because look at this, you've got something which is of the order of 1 million. The UK population, I think, is about 60 million. So this maybe give you some idea of actually how many people may have the disease. Of course, it could be factors of 2, 3, 4 out, depending on what these numbers are. And of course, these numbers will vary probably considerably between different groups. So again, take this with a huge pinch of salt, but nonetheless, at least it gives you some idea of how we can use a gradient method to get from something which we're fairly certain about to something which we could not measure, because you can't test everybody, but gives us an idea of how many people may have had the disease. And now you can start to see the peaks and the troughs, etc. And you can see, I think this is the second wave. So when vaccine starts to come in, look at this lower part here. This information could potentially, if it was properly scaled, useful for people making policy. So there we go. That's probably until recently, the largest issue of our time. Okay, so going back sort of more mathematically about sort of finding gradients, etc. So here's a sort of problem that you might have at school. So 4 minus x times x squared, that's a cubic. All right, and might be asked to plot this. That's the blue curve. We know that it's got a 0 at 4 and a 0. And we've got the sort of a maximum and minimum we can find by differentiating this, expanding it out, and working it through. So you can do this, obviously, but you can also maybe use some software to work out what the tangents and normals and indeed the derivatives are at any point. So software like Desmos, which some of you might have used, Wolfram, and indeed good old MATLAB, which I like to use, we can actually work cubic splines across the curve and actually evaluate it numerically. And so that can actually help us to sort of check our answers if we're doing some pure maths. So there we go. So all these are evaluated numerically. So the gradient of my blue curve is the sort of purple curve, df by dx. That's f of x. And this is sort of an example of if we take some data, how we can fit a cubic between the points. So there we go. So there's another, even though we've looked at examples which are in the real world, we can actually help ourselves out if we're doing pure maths as well. Quick question, what is partial differentiation and what are its applications? Partial differentiation is if you have a function of lots of different variables. So rather than x there, let's have that to be z or something like this. And partial differentiation, you can kind of imagine, you know, maybe sort of like a hill, a function of sort of x, y, and z. You know, sort of z is the height of the hill. And you're looking at a gradient along a certain line, maybe the x equals 0 line. So for partial differentiation, all we're doing is treating all the other variables as a constant and then differentiating it in the normal way. However, so this is not really a maths lecture. We're not really going to talk about the methods of how we can find the gradients of a functional expression. It's more that how we can do it with a spreadsheet that can help you out. Okay, so we've looked at finding gradients. So let's go the opposite process and find some areas. And this is Leibniz's notation for finding the areas, which is what we call an integral. And literally, it's an Old English sum of the height of a function times a little bit of its width. In other words, a rectangle. And literally, it is what it is. It is what it says it is. Okay, so how can we find areas? Well, these are some nice numerical, a sequence of numerical methods that you might want to have a think about. So let's just say here's a curve here. The first thing I might want to do is take the midpoints of all. So I divide things up into strips. All right, remember our expression is the height of the function times its width and summed. All right, that's what it is. And the implied part is that bit dt means I'm taking a magnifying glass and I'm making my strips as thin as possible. In fact, in the limit of the strips become infinitesimally small. But when we're doing numerical methods, we're assuming our strip width is a finite small quantity. All right, just like when we worked out the gradient, that the time interval between our velocities, etc., is a small but finite interval. So a midpoint method, I basically take the middle point between our data and work out the strips. You can see it sort of, it's not a bad estimate, but it's not completely hugging the curve. I'd have to make my strips a bit smaller for that to be the case. I can do a better job by doing trapeziums. So literally drawing straight lines between my points. And you can see I'm overestimating the curve here and underestimating it here, depending whether the curve is a sort of happy face or a smiley or an unhappy face. Okay, so that's a bit better than this one. I can go even better if I fit quadratics between the curves. That's called Simpson's rule. This is called the trapezium rule. And I can go even better still. I'm going to give a smiley face for this one if I fit cubic splines between the data points. So this curve is a slightly complicated thing involving sines and exponentials, just to get a bit of a wiggle there. And that's pretty close to what it actually is. All right, it's hard to see the difference. So there we are. All of these are numerical methods. Harder to code this one than this one, but nonetheless, that gives you a way of finding the area under a function without having to do any complicated mathematics. Some things, even if you can write them down, cannot be integrated. All right, it's a little your teachers will torture you by asking you to do some nasty integrals, and some you cannot do yourself, but you can do numerically. So here's before we go into another practical example, let's just show some software, how this works in practice. So there's loads of programs that will do this. Desmos is pretty good. This is one of mine. So this is done in MATLAB. And here's a function x sine x. That's the red curve here. And I want to work out the area difference between the red curve and the blue curve. And I've got minus sine x, which is the blue one. And I've set that so they cross the axes at the same points. Basically, I can work out the areas of this. Now, I can actually do this analytically. I'll leave that as a little exercise to you to find out the difference between these two things. If I go between 0 and 2 pi, I work out this value here. In fact, it's minus 2 pi. In fact, is the answer. And there we are. So it's a minus sign because if we go below the axis, our areas count negatively. and there we go. That's our result. So I'm doing this by working out my cubic splines, and then finding out what the areas under those are, probably by my sort of a cubic spline integration, because integrating a cubic will give us a quartic. So there we are. So we can figure it out, but we can easily do that with trapeziums or whatever, as long as we have a sort of small enough interval. So that's quite a nice thing to do. Right, let's have a look at how we might apply this to some physics examples. Right, okay, so here is a very, very old and slightly knackered basketball. Sorry for the dubious colour, it's a very old and ancient one. So the reason we keep this in my laboratory is that it doesn't bounce off the desk. And what we're trying to do is show that momentum is conserved. All right, so we always tell you this is true, and you do lots of calculations, but how do we show that it's true? Well, we should be skeptical, ladies and gentlemen. So we can actually measure this effect in the laboratory. This is a force plate, and the reason I have a flaccid ball is that if it's a nice, fresh, brand new bouncy ball, it will bounce this and bounce off the table and become a bit unwieldy. Whereas this flaccid ball just tends to come to rest after bouncing a few times. This is an ultrasonic position sensor. So ultrasound, something above 20,000 hertz, will bounce off the ball, and we can work out the distance of the ball as it falls. And if we know the distance, we find the gradient of that curve, we find the velocity, and for the gradient of that curve, we find the acceleration. So what we're trying to find is the integral under the force time graph. That's the change in momentum. Why? Because force is the rate of change of momentum. So let's go and see what happens. So here we go. Here's our little sensor. It's like a fly's eye. This is our Pasco USB data logger hub. Slightly more modern versions are available these days. And this is our force plate. So let's have a look. Well, here's position versus time. And what we can see is some lovely parabolae here. All right, so this is when the ball is basically rising up, and then falling in under gravity. We can ignore air resistance. It changes direction, of course, because it's bouncing. So positions measured from the top of the sensor. So, it gets to this point here when it hits the force plate. All right, now if we plot velocity versus time, what do we see? Well, we see a series of straight lines with a bounce in between. What's the gradient of this? Well, it's going to be g, 9.81 meters per second squared. So there we are, a lovely way of measuring g directly from our data. And how have we got this one from this one? Well, we've numerically differentiated it. So if we do force versus time, when the ball is just sitting there, that allows us to measure its weight. So we don't really need a mass balance. It is one. So there we are. We can measure the sort of weight of the ball, and hence there we are, 6.13. And there we are. And so from this force versus time graph, so I don't know if I've got the force versus time graph. Oh, I haven't got one. Okay. Well, I'm zooming in on force versus time. If we zoom in, we'll get a whole series of sort of spikes for this one. Whoops. And because the force versus time, we're recording at what, sort of thousands of times a second, roughly. So 345, 335, yes. So really, really tiny, a small area of time between our points. So as it bounces, we can work out the force versus time. And what we should find is, if we find the area under that, which we can do a trapezium rule. So we are writing out these little trapeziums. So that's the base times, so it's a sum of the two heights times the width of the trapezium divided by 2. So we sum all of those, which we can do in a spreadsheet. And that is essentially numerically integrating force with time. All right, so we're using a trapezium rule. And if you add them all up in a spreadsheet for one bounce, you'll find it's about 3.78 Newton seconds. All right, so that should correspond to the change in momentum as it bounces. So if we look at the velocity versus time graph for the first bounce, what do we find? Well, it's where's the bounce? Well, probably about here, about 4. And if we find out the difference in velocity, we've got about 6.1 meters per second. So it's heading towards the force plate and then rising up at that speed. So if you work out the change in velocity, from there to there and multiply it by the mass, you'll get about 3.8 Newton seconds, which is very similar to what we got with integrating the force versus time graph. So numerically, we can find the correspondence that we keep telling you in physics, that the force is the rate of change of momentum. Well, we can measure force versus time completely separately from velocity versus time and show that the impulse of the force plate on the ball is the same as the integral of the force versus time of the force plate on the ball. So hopefully within the bounds of error that physics seems to work. Okay, there we are. Right, something a bit more complicated, but nonetheless interesting. So this is Stefan's law, which is basically if we've got a body of temperature T in Kelvin, then the power per unit area that's radiated from that goes as T to the 4. All right, really interesting law. So if we double the temperature, we have the radiant power goes up by a factor of 16, 2 to the 4. And that constant in France is called the Stefan-Boltzmann constant. Now, for those of you who studied a bit of quantum mechanics, what you find is that this comes about because of a curve, the Planck curve. It's called the irradiance. So it's in watts per square meter per nanometer. All right, so it's the power if you plot it against wavelength. And what you'll find is that every sort of hot body at temperature T will have its own characteristic Planck curve. It's got quite a complicated expression. There's some B's, what I call the irradiance, and it has a 1 over lambda to the 5. It's got this exponential thing involving the temperature downstairs. All right. Now, what's really interesting is it has this number H, letter H. That's Planck's constant. And in order to work out that curve, you have to find that light waves, all right, are quantized. So energy comes in packets of HF. H is Planck's constant, which is this 6.63 times 10 to the minus 34 in standard units. Really tiny number times the frequency. So this is the fundamental idea, the quanta in quantum mechanics. The energy, light energy particularly, comes in wave packets, comes in little quanta of energy. So the analysis, which is very beautiful, that sort of I can point you to a nice little resource. Einstein is, I think, this probably did the analysis. You can work out this curve. Now, what's really interesting is that the area under that has got to equal this, because this is the energy per unit area radiated. All right, this is the energy per unit area per wavelength. So the area under that curve, this integral here, so the sum of B multiplied by a little bit of wavelength, summed from 0 to infinity, must give you this. And although that sounds like the hardest thing in the world to do, with various tricks, it is possible to actually integrate that. And indeed, you can show that this is true. A lot of transformations required a variable, and that gives you the T to the 4. And then there's some standard integrals which you can use, which produce, interestingly, pi is involved, all right? So you can work out this constant, Stefan-Boltzmann constant in terms of the speed of light, Planck's constants, Boltzmann's constants, and pi, amazingly. And that must have been very, very pleasing for Mr. Planck and others who did that for the first time. So can we show that this works? Well, the idea is this is real data of this irradiance curve measured from satellites outside the Earth, and the sunlight peaks in the visible spectrum. It's sunlight after all. So this is the range of visible light from purple to red. Obviously, there's quite a lot of radiation in the infrared and also in the UV as well. What would be quite nice is to actually numerically integrate that and see how it compares to what we predict for the Planck spectrum. So if you actually work out the area of all of this, and I sort of work out all of these, this is what this is just working out the function itself, and sort of add them up, and we get a predicted value of our solar temperature to be very, very close to what it actually is. All right, so what we can do is we can work out this sort of integral here, and we can use that to work out what the temperature of the sun is. How have I done this? Well, if you look at that, if I just zoom in a little bit, here's a spreadsheet. What is this all about? Well, if what I call big phi, right, is the actual sort of flux itself, this is the power per unit area. This is sigma t sun, the little circle with a dot in it, it means the sun. So that's the power per unit area radiated by the sun. I've got to multiply that by the surface area of the sun. And so the thing on the top is the luminosity, a total power radiated by the sun. And so if I want to get the power per unit area received on the Earth, I've got to divide that by a sphere of radius 1 astronomical unit, which is the Earth to Sun distance. This number here, 1.49598 times 10 to the 11 meters. So if I rearrange that expression, all right, I know what 1 AU is, the radius of the sun. Let's just say I know that it's this number of meters. I can work out what the temperature of the sun is. So I can find out this thing by working out this sort of quantity here, and I indeed get a very similar figure for the temperature of the sun. So there we go. There's a slight gloss over fact here. There is a mistake in this spreadsheet. Maybe one of you can find out what it is, but for some reason my Planck curve that I've coded, I can't quite match this one. I don't know quite why the height is not scaled properly. It works when I do it in MATLAB, but there we are. So essentially, if we get the temperature right, that we should match our data to the curve. So like this one here, the black curve has the 5778 Kelvin is the official version of the temperature of the sun, and you can see it sort of fits the data really rather nicely. Okay, so there's another example where we might want to integrate something. You never know. We might want to sort of find out the temperature of a star or some information of that just by its irradiance versus wavelength from, say, spectroscopy. Although there is actually a quicker way of doing it called Wien's law. If you take the peak of this, you'll find that that is related to the temperature as well. So there we are. If you know the peak wavelength and the temperature, you can actually find out, we can find one from the other. So there's some examples of integration, and that's kind of concluded our sort of very quick tour. So yeah, I think this might be an opportunity to just take any more questions, if anyone's got any. Nope. Okay, so I think we'll just look at the chat. Is anyone there? No, that's all fine. So as you probably noticed, this course actually has a little book which goes with it, book called Science by Simulation, which will be published by World Scientific very soon. We're offering several books as a prize for the best 5 the challenge entries. So remember, in a few weeks' time, we're going to release the challenge for this course. Let's sort of bring up that. So if I go to my website for a moment, so here we are. You can access this from the BIFO website or from my Eclecticon. So if you want to sort of take the web address of this off the screen. This also allows you to access all the videos. So the YouTube videos are these recordings, the data itself, and in fact the presentation. So we're at number 7. So we've got 4 more to go. We're going to talk about gravity sims next time, and then some randomness, and then chaos, fractals and all sorts of things, and finally rounding off with epidemiology. And all of these things that we've been discussing in this course are related to this book, Science by Simulation, which you can order from World Scientific. There might even be a discount code soon. As I say, it will be a prize for the challenge, which will release very soon. Just to kind of give you a little bit of a flavour of this book, we've got, so there is a page of Science by Sim under sort of physics, Science by Simulation, and yeah, so this first book has all sorts of things: chaos theory, atmospheric physics, fractals, epidemiology, and also some calculus methods as well. So hopefully should be a nice companion for university stuff. we've already got a few minutes left, so I'll give you a little sort of summary of what that might be. Let's have a look. I should have, here we go. So 2-minute summary. It may not be quite 2 minutes. There will be a video coming soon. So this is the title of the book. You might notice this from the splash page for the Eclecticon. And essentially, there are 3 parts to this book, which really we've been exploring with this course all the way from the beginning. So we've got the power of context. So things like Bezos's launch, Usain Bolt's 100-meter race, epidemiology. We'll start with the plague in EAM, but we can look at Ebola and we can look at COVID as well. And really, to make a sense of this, we're learning to build computer simulations. We're building spreadsheets, and then as we get more and more adept, we're building MATLAB, Python, whatever, coded models. So here's a few nice little examples. This is the snails of pursuit. So we've got some snails here. This is, I think, the first problem in Gnardeg's lovely book. Essentially, the snails are attracted to each other's gastropod perfume. They can all travel at the same speed. So what happens to the snails? So if we have a pentagon of snails, they will retain their pentagon shape, but the pentagon will rotate and shrink. And you'll end up with these rather beautiful trajectories, logarithmic spirals. And amazingly, you can actually work out how long it takes the snails to get to the middle very, very, very simply. It's literally the projection of that velocity onto these fixed angles. This is election cups, which is a little practical I devised a few years ago. It's a bit like Eliza, there's a hole in my bucket. So we did this with the Olympiad training camp last year. So essentially, we've got different holes in each of these sort of metal shot glasses. How long does it take to sink? So it's a really fun experiment to do. What you find is it's an inverse square law. So as the hole diameter doubles, the time it takes to sink will quarter. And you can do a line of best fits. All this, if you've been on this course for a while, all the techniques we had at the bottom. So I'll just give you a few other things. This is all about EAM, and we've got infectives, susceptibles, and the doomed for the plague spreading in Sheffield. All sorts of stuff. So that's very much the first chapter. Let's see if I can find a colourful one. So there's the COVID stuff, some fractals, the Lorenz attractor. We'll cover this in a few sessions time. And here's probably the most pretty stuff, which is the Mandelbrot set, but perhaps a Mandelbrot set that you may not have seen before. So there we are. Here's the Mandel plant, and these are the Mandelbrot variations. So we've got sort of light bulb, we've got a sort of rocket ship here, and we've got the sort of here we are, the 7 steps to enlightenment. So there we are. I'll leave you that on that sort of psychedelic note. Do come next time, and we'll look at gravity simulations. So we'll look at something that looks a bit like. I don't have the gravity simulations here. Never mind. Anyway, so we'll see you next time. Thank you.
Andy, we've got some questions. Do you think you've got 5 minutes to answer
Yeah,
them?
sure, absolutely. Go for it.
Yeah. If you click on the Q&A, you can pick and choose 1 or 2 of them. Right.
Okay. So, could you give an example of what the challenge would be like? Right. Well, sort of. Without kind of giving it away, there's going to be a series of problems we'll set. It would be like a model. So, I don't know. Let's just say, let's bring out one of these. This won't be the challenge, by the way. But let's have a look. Where's the radio? Let's go for this one. So here we are. So this is a model of a rainbow. All right. So the sun's rays, hit the water droplets. This is what happens. They bounce off the internal surface and come back. And the trick is to find the model elevation versus angle of your rainbow. So if I'd set that kind of thing, we'll sort of ease you through the model, and there'll be a kind of bronze exercise of maybe working out how these angles work in a spreadsheet. And there'll be a silver one which may be a bit more complicated, and then a gold one which may be making an app of some description. So actually, I'll use the epidemiology example as a good one. Again, I'm afraid that's not the challenge. You know, so for example, yeah, here we go. So if so here we are. So a bronze example. In the epidemiological model, we have a formula for the rate of changes of susceptibles, infectives, and the dead in terms of infectives and susceptibles. So these equations here, we can actually code up, we can evaluate numerically using the techniques we've kind of been doing recently. You can basically use a spreadsheet to do it. So that will be, well, you'll be guided through it, but essentially producing the spreadsheet will be the sort of bronze level. So how do we work out these curves, for example? How do we build a spreadsheet that's like this and write it up? A silver level will be a bit more detail, maybe working out what the numbers are for this. And then the gold level will be, well, can I make an app with this thing? How can I have a model for this working out what the curves are? As I vary various sliders, you know, I could do this is in MATLAB. You could easily do something in Python at the same time. So that's the kind of thing. So you know, the challenge will be, you know, I'll set a series of problems, but the sophistication of how you solve them will depend on sort of what level you will go for. And remember, the solution is to make a YouTube video of how you've done it. The tool is up to you. Okay, so how do you get irradiance data originally for the Planck curve? Right, so I'm not quite sure exactly what you mean by that. So the irradiance data, so this was, let's just get out of this. That was originally for, let's have a look, this one. Yeah, so the blue splodges here, the blue stars, that's data which you get from a spectrometer. So you have a satellite in space looking at sunlight and seeing how much power you get per unit for a unit area of your solar panel for each wavelength of light. And that's how you get the blue data. It's a little bit noisy around the peak, but it does pretty much follow this Planck curve. How do we actually get the Planck curve itself to derive this? That's a more complicated story. But if you're interested in that, if you go onto the eclecticon, so there we go, there's the eclecticon. If you go onto physics, to notes, nuclear particles and quantum, and what we call black body spectra. So hardcore maths alert. But if you really want to know how it all works, I take you through the derivation. It's something that you'll do, you know, there it is. It's all the guts are there. It's not too bad, but yeah, you'll certainly do that first year university. But if you want to get ahead, you can access the notes for this all here, and much more besides. Any more questions? I think that's it. Good. Well, thank you very much, everybody. We'll see you next week for more of the same.